Evening to all of you who have joined for this lecture 48. And today I'm very happy to say that we have with us an outstanding teacher, researcher for excellence, and that too in core area of mechanical engineering. He is no other person than Professor Pradip Dutta, who is the Professor for Center for Energy Research, Department of Mechanical Engineering, Indian Institute of Science, Bangalore. Today, he is going to talk about transition to clean energy, new R&D opportunities for engineers. Before giving you some idea about the abstract of his talk, I would like to say that Professor Pradip Dutta he has received his undergraduate degree from my alma mater, IIT Kharagpur, master's from IIT Madras, and PhD from Columbia University, New York, all in mechanical engineering area. He has been elected a fellow of ASME, ASTFE, and fellows of all 4 national academies, that is INSA, Indian Academy of Science, National Academy of Science, and of course, the National Academy of Engineering. He is a teacher for excellence, and therefore, he has got also prestigious award from Indian National Academy of Engineering as distinguished teacher. He is also Jesse Bose National Fellow and past president of the Indian Society for Heat and Mass Transfer. So we'll listen to him and interact with him. Now, the abstract of his talk is on transition to clean energy and new R&D opportunity for engineers. Today, the world is facing a major crisis in the form of environmental degradation and climate change in view of the government's international think tanks and policymakers are framing new regulations to phase out conventional greenhouse gas and greenhouse gas emitting technologies and give way to new technologies and practices to arrive at a net zero emission target within a specified period. These new policies and regulations are leading to disruption in energy production as well as in energy uses, with greater emphasis on cleaner and renewable energy production, electrification in transport sector, and decarbonization of industrial processes. His talk highlights the global trend in clean energy implementation and analyzes some of the alternatives being pursued, new R&D opportunities, scope for indigenization, and critical use of core engineering disciplines such as mechanical engineering in the transition process are also being discussed by him. In addition, some R&D initiative taken by the speaker and his research crew will also be highlighted. Now, as you all know, that this series of lecture is conducted by INA Bhubaneswar chapter with active support of IIT Bhubaneswar, IIMT Bhubaneswar, NISER Bhubaneswar, SWA University, and IEEE Bhubaneswar chapter. So, because other institutions find it difficult, so they are not always actually in a position to come. So, I will, if Professor P.K. Nanda, our Vice Chancellor, is present, may give some initial remark. Professor Nanda, are you available? No, I think he is actually stuck somewhere. So now I'll request Professor Dutta to please begin your talk.
Thank you, Professor Acharya, for inviting me to this forum. And I would also like to thank the INA Bhubaneswar chapter for this wonderful initiative of a series of lectures. I think we all learn from each other from this kind of forum. And IIT Bhubaneswar, I mean, the Bhubaneswar chapter of INA has been quite active in getting people in various fields, so that there is a wide scope for learning from each other. So I will first share my slide to bring up the title of the talk. One second. Yes. It's full screen now, right? So, when Professor Acharya requested me to give a talk on this forum, I was wondering, what to talk about. Then I realized that it's an opportunity to, talk to experts from various backgrounds. So instead of talking only about our own research, which goes on in the lab and with our group, I would rather, present something which may be of broader interest to everyone, based on the exposure that we have had until now in the field of energy and sustainability and the development of technologies related to this. This is a very very big field, not just for research, but also for policy making and for the think tanks to come up with new regulations and so on, because it's a very fast evolving field that's happening in this world now, the transition to clean energy. And it is so vast that I personally am not very qualified enough to talk about all the things that are happening in this field, and I'm not also well exposed to everything that is going on. So some of the views and some of the material that I'll be presenting for discussion may be limited in nature, but it nevertheless will point towards a certain direction that the world has been taking, and it is continuously evolving. So what we think today and we are saying today, few years down the line, it may be different. So we have to take it in that spirit and move on. And from an R&D point of view, there are always new opportunities that are coming up. So in this transition, many times, the core engineers feel that we are, we are losing the ground towards new things. So what will happen to us? But it is actually just quite the opposite, because as the field is evolving, as the scenario is changing, and more new opportunities, and all of us have to really contribute towards it, adapt and contribute. So with that, let me begin the talk by first the highlighting uh, highlighting what are the clean energy routes. When we talk about clean energy, we normally think of clean energy production, that is shifting from coal and oil to renewable energy and so on. But that is not enough. There are uh, yeah, there are two other aspects which we should not miss out. One is the energy usage. And when we are talking about usage, we normally would have two vectors. One is through the electricity usage, that is after the clean energy is produced, and the other vector is fuel. Hydrogen is one example, but there can be other forms of fuel which you can call as clean fuel. So, and the other thing that we need to know is that when we are looking at renewable energy, which may be fluctuating in nature, storage becomes an important component to the energy mix. And when you're talking about energy usage, see, it is not just enough to get clean energy, but we need to use the clean energy in wherever energy is being used, especially in the industries and domestic sectors and so on. So that's the field which is now called coined as decarbonization. So I will touch upon many things, but as I mentioned that I will not be able to cover each and everything, but just give a some kind of an idea the way we are understanding how the area is evolving. Now, when it comes to energy supply, uh, the Indian scenario is as we see here, the coal and oil and gas, it is still growing. As we see here, this is the coal and this is the gas. Uh, Nuclear is not growing much, as we have seen, but there is a lot of scope. And the coal and oil, they are still a big share. And renewable has started off and it is expanding very fast, but still the share uh, is not that big yet. Uh, Now, when it comes to clean energy production, from a universal point of view, there are these COP meetings which are held every year. One meeting, COP 29, got over just last week in Azerbaijan, and this was COP 28. And resolutions are taken, agreements are signed, and COP 28 in 2023 in UAE, the resolution was that beginning of the end of the fossil fuel. Um, so this was, and there was an aggressive push for renewables, and a target date has been set for phasing out fossil fuels. And even in other conferences, where the Solar World Congress, which was held in Delhi last year, there was a special roundtable theme called "Moving the World Towards 100% Renewable Energy." Now, all these are easier said than done. That shifting from the usual energy sources to the completely renewable energy source, it's not so simple. For instance, if we look at a study by NREL, National Renewable Energy Lab in US, in 2020, there was a projection that if we have to move towards fully renewable energy, then what could be a possible energy mix that we would have? So this is just one such scenario. So this is at 2020, this was the present scenario where uh, we would say this is the fossil fuel, the black color is the fossil fuel one. And then there are other, like this is the wind, this is the solar, this is a worldwide distribution. And then if it is projected, fast forwarded to 2020 to 2035, with the current practices and policies, then the scenario will not change that much in terms of fossil fuel. But of course, the solar and the wind components will become much larger. Fossil fuel will shrink a little bit, but not by much. Now, if we have to say, let's say 2020, 2035, which was the target put in COP28, that everything has to be clean energy, then this was a possible mix that was projected. And if we see here that everything is not solar, in fact, the wind is more than solar. And we also have other ways of producing hydrogen and having some energy in the form of a fuel. Of course, here the renewable component has not been shown in a big way, but this is one of the energy mix projections that was done by NREL. Now, what it means here, the message here is that the solar, when we talk about solar electricity, we are talking about the solar panels, which is the photovoltaic. Now, because of its fluctuating nature and the share of it, not more than 30% is normally recommended. Otherwise, there will be grid instability. The wind share can be a little bit more because it is more stable, but we need some kind of a fuel or grid stabilizer which can act in the form of a storage. So all it means is that when we want to shift from the usual energy to clean energy, especially with renewable, we have to keep in mind about the grid and about the storage as well. So now what is happening in India, if we see, this is just one of the statistics that I have obtained. This is a 2022 scenario. Let's say this is the wind and this is the solar. So if we see the 2015 solar was not much because the prices had just started dropping. Around 2012 it started dropping, and the wind share was more. Then the solar started picking up. Solar panels. And then, of course, there was a dip in 2021. And if you see, there is almost a steep rise of the new. These are all new installations. These are not the total installations. New installations, if you see, there's a steep rise in this solar panel, but there is actually a dip in the wind. What could be the reason? The reason could be that solar PV maybe is more profitable in the sense that the investors would like to push it more because it is a more sustainable from their business point of view. It is. So it's not necessarily sustainable from an environment point of view, but from the business point of view. But when we are talking about sustainability, we are looking at the cost. Now, what is the real cost of renewable energy? Because what we have seen here, for instance, it's just because the cost of the solar panels went down, so the investments went up. Okay. Now, when we are talking about cost, we should not forget what is the real cost of the renewable energy, because the real cost is not the cost that we are paying. Of course, the source of the energy is free. The source of the energy is free, and now when we are talking about cost of renewable energy, the governing principle comes from our good old second law of thermodynamics. Now, why does that happen? Because energy is not just energy in terms of watts or joules or kilojoules. It has a quantity as well as a quality, which means there is a grade. And when we have renewable energy, because of the very low intensity of solar radiation or the wind speeds, they are classified as low-grade energy and electricity. Now, to convert them to electricity, which is the highest grade of energy equivalent form of work, because it's in the form of work that we are using electricity in vehicles and any other motive applications. Now, to generate electricity from the renewables, we have to convert from a low grade to the high grade. And so therefore the efficiency can be quite low and limited by the second law. It's not just in thermal, but in every other ways. The same principle applies in a different way, though. So we need to concentrate the low-grade energy to convert it to the high-grade energy. So we need large amount of land, large amount of material. For example, in the case of solar thermal, it's very easy to understand what we mean by concentration. We have the low-grade sun's rays here. We concentrate the energy to bring it to high-grade, which means that we use big solar collectors, and they will concentrate. High temperature is produced, and when high temperature is produced, we can use that high temperature to generate electricity, which is the highest grade of energy, with some factor called efficiency. Now, the similar thing is also in the photovoltaic. We are converting the low-grade optics, solar optics, into electricity. So we have to invest in the materials for the conversion. Similarly, in the case of wind, we are investing in the large turbine system, which is catching the low-grade wind energy and then converting it into high-grade by concentrating it right where the rotors are. So what it means is that we need to invest in material, and when we invest in material, it gives rise to capital cost, either in dollar or rupees or whatever. And it is this capital cost which determines what would be the cost of the energy that we are paying for. And when we do that, we do it in a sense called levelized cost of electricity. For instance, in the case of fossil fuel, it is mainly driven by the cost of the fuel and less in the cost of the infrastructure or the power plant cost. Whereas in the case of the renewable energy, it is actually the fuel cost is zero, or the running cost or operation maintenance cost is much lower compared to the initial capital cost, because you have to invest in the material. So that's why if a plant is designed for a life of about 25 years, the cost of per unit of electricity that we are paying today is the levelized cost over the entire lifetime of that plant. That's we have to keep in mind. Right. So that is as far as the cost is concerned. Now, if you look at that levelized cost, how things have changed since 2009, the levelized cost of the solar panels was quite, high at that point of time, because the solar PV was expensive. In fact, the wind was much better, and solar thermal, which is this line, was actually much more attractive than solar panel. But around 2011, which is mainly because of the production in China, the scaled up production, efficient supply chain management, and other subsidies that were given, without any real new technologies for the solar PV. It was a well-proven polysilicon based solar PV that was introduced and scaled up. So they brought down the cost drastically around this. Of course, their planning had started at least about 10 or 15 years back before this kind of a plan. And then once this price has dropped, right, if you see, then the investment in the solar panel based big PV plants picked up. And that is where we are today. And wind is been steady in that sense. And here we are. Here we are. So what it means here is that this is whatever we are investing on, or the trend where the world is going, is based on the levelized cost of energy. But what is the real cost to the environment? That is rarely taken into account. Now, one of the matrices, which is called also one metric of sustainability, is energy return on energy invested. And there are other matrices as well to evaluate the sustainability part of it, and not just the cost that we are paying out of pocket, cost of the energy. Now, energy return on energy invested is that what is the energy that a plant delivers in the entire lifetime divided by the energy required to deliver that energy. Now, when we say energy required, means that right from, let's say we want to make a solar panel plant, right from mining of silicon, processing, and all the way to production of the panel, and then its entire, the circular economy, that is all the way to recycling. what is the cost that is in what is the energy that is required for in its entire lifetime, which is based on a life cycle analysis. That is what comes over here, and this is the energy that is delivered over the lifetime. So anything more than one means that it has delivered net energy. Now that's not enough. More than one is not enough, because then the whole exercise is a zero sum in that case. So this EROI should be much more than one in order for a successful and sustainable energies to define a good energy source. We need this EROI to be much more than one. And these are the EROIs that are there. Of course, nuclear is the best, actually, because the energy it produces divided by the energy that is energy required to set it up in the first place, in its entire lifetime, whatever energy it consumes, is nearly about 75. But of course, and it is also clean in the sense of emission, but one has to take care of safety issues. Hydro is also very good, and these are the fossil fuel based ones are also good, but they emit CO2, so obviously they are not welcome here. And within the renewable ones, if you see, is a solar thermal which scores much higher. Of course, these numbers can vary depending on the type of life cycle analysis one does. So solar photovoltaic may be ranging from 2 to 4 or 5, and there are even more rosier pictures. Biomass can also have different numbers, but I have looked at many analysis, out of which it turns out that in general this is better. But the reason this is not adopted is that it is not scaled up to the extent these PVs are. So the cost of investment is much more at the moment, and that is why it is not. And the break-even point from what the social scientists analyze is that the break-even point should be 7 or more. So which means that these are the ones which score much better than then. But we are now moving on with the others, because the LCOE, the levelized cost of energy, is proven to be better in this case. Now, going back to this LCOE, that is levelized cost of energy, if you look at nuclear, it is quite high, and it is going up also, because a lot of it is because of the environmental regulations, and also it is not that well scaled up in the supply chain. So this has to be pushed up. And in our union budget declared this year, there was a big push for small modular reactors. And worldwide, there are many countries who are thinking of increasing the nuclear share of nuclear energy in their energy mix. Now, solar thermal is another one which should increase, but it needs big investment. It does not necessarily need new technologies, but new technologies can improve the performance definitely. But it needs big investment like what PV had, to create the ecosystem and the market for manufacturing to lowering cost. And already, actually, China has already started that initiative. In the past 7 or 8 years, they have been working on it in the CSP. And what they're trying to replicate the PV story. Because this is not very well known to everyone, but if one looks at this source is NREL, they have seen in their document, it is shown that there are many plants which are coming up in the Gobi Desert of China, where it is quite cold, and the solar DNI is quite high. So it's an ideal combination. What they are doing over there, instead of creating a big solar thermal power plant on its own, they are basically, from a cost point of view, solar PV is quite beneficial. So the large part of the plant is actually solar PV. And a smaller component, but with nearly about 24-hour storage. So PV is without the storage, and this is with the storage, right? So what you see as 100 megawatt is actually maybe is producing energy 4 times that compared to, I mean, what is the nameplate energy capacity here is 600, but it will produce 600 without the storage, which means that 1/4 of the day or 1/3 of the day it's only operating, whereas this will be 24 hours. So in that case, what happens is, what they are doing is they are doing a hybrid power plant, and that will ensure grid stability. And what it will do is, overall cost, they are trying to keep it down because the solar PV cost is quite low. And this one, they are introducing it instead of big battery storage for the grid stability. They are doing it through power generation in solar thermal. And on top of that, what they are doing is they're creating a market by declaring, by initiating all these plants and this big investment. They're creating a market for their manufacturers to scale up their manufacturing and the machines and everything. So which means that in a few years down the line, it's possible that the cost of these solar thermal components will come down, just like the way they had done for the PV. And this advantage is that it comes with the storage, so there is grid stability. And when you look at the cost with storage, then they are comparable anyway. Even today, they are not too far away. So that's the type of investment. And then hybrid with wind and CSP and PV. There are other types of plants which are coming up now, and some of them are already operational. You see. So with that, let me shift to a little bit time I'll spend about our own research at IISc, which we have been doing towards the solar thermal. Just a few slides and on new power cycle, supercritical CO2 Brayton cycle. So this basically is a new cycle of power plant to replace the steam-based power plants for higher efficiency and modular in nature. So they are scalable, and they are ideally suitable for nuclear, the solar thermal, and for waste heat recovery. One can have higher efficiency, lower footprint, smaller footprint, lower cost, eventually when it is productionized. So these are the advantages. So we have built, Professor Pramod Kumar, who is also a fellow, he has in his lab developed this. It's the first fully working Brayton cycle test bed for supercritical CO2. In fact, only one in the world which is working end to end. Otherwise, in Sandia National Lab, they have only the compression part which is working. And there are other parts in the world, like Australia, Germany, they are working only limited part of the cycle. But this is the first fully working Brayton cycle test bed. And an important part of it was development of a turbo machinery. In the supercritical CO2 turbine is not there in the market. And with Triveni Turbines, which is a Bangalore-based company, they manufacture steam turbines normally, but they have undertaken a joint project because DST has supported quite a bit in this venture. And the turbo machinery is also developed and now being tested. And along with that, high speed, because these are all like 50 to 70,000 RPM or nearly a lakh RPM it would run. And the corresponding generator also is developed. It's a switch reluctance generator. This was part of the imprint project. And then also printed circuit heat exchangers, which are required for supercritical CO2, the Brayton cycle. There are only two manufacturers in the world. One is Heat Trick in UK, and the other is Vacuum Process Engineering in US. And the cost is very high when you want to order anything from them. Now that has also been now indigenized with the help of support from DRDO and other agencies. That manufacturing process also has been developed, as well as the design process of such heat exchangers. So these are some of the ventures, and also the high temperature receivers. Also, we had some projects under the Indo-US program, and then through MNRE, we have developed high temperature, high flux solar simulator. These are only high flux solar simulator with a concentration of nearly about 500 to 1000 can be achieved over here. It's only about 2 kilowatt of heat that is generated over here, but with concentration. And then with BHEL, we have developed high temperature solar receiver material. These are ceramic based. And with Sandia National Lab also, these supercritical CO2 receivers. And with BHEL, we have also, okay, these are other receivers that have been developed at IISc. I will not spend too much time on these right now. But with VHL, we have also developed high temperature thermal storage systems, which also goes. These are also ceramic based, using natural material, mineral based materials like viewlight. And they have been tested for charging and discharging. Right. So these are some of the things that we've been doing. But again, there's so many things which are happening in every kind of field. Now, going back to energy usage, again, now we are coming out of our own research, energy usage, sector-wise, if you see that if you look at the industrial sector is quite large here. Now, why we are going to do that, looking at these statistics is that if you have to target, where to save CO2 or where to cut down the CO2, it is not just in the energy production. Also in the energy usage, if we can cut down, then there will be a comprehensive approach towards lowering the CO2 emission. So otherwise, only energy generation part, if you take care, it may not be enough because industrial decarbonization is also a big part. So when you're talking about energy decarbonization of the industry, now this is another big opportunity for core sector engineers, especially for Indian industries. We have started the process, but it's a long way to go now. So the processes, now something like steel plant, for instance, from a carbon-based approach, like the coke-based, to something like hydrogen or electric arc furnace in large scale, it's a big change. So decarbonization is based on carbon or CO2 free primary energy sources is one thing, and for instance in the mobility sector, it would play a significant role in determining the sustainability of the future, electrification of vehicles and other industrial operations. So the electrification is another route for decarbonization, and but that's not the only route. The reason is that for the electrification, the infrastructure for all the user sectors are available or possible. Long distance high voltage transmission is also there. So if you generate the green electricity through renewables, it is possible to have access to that electricity at every place because of the infrastructure that is already there. But when it comes to transportation, for instance, and we are talking about the EVs, the one thing that I would like we are talking about, what are the new opportunities? The shifting from IC engine vehicle to other forms like EVs or hybrid EVs, it doesn't necessarily mean that an engineer like mechanical engineer would lose jobs, because this is the kind of notion that has been there, and as a result, suddenly young people are thinking that I have to leave my field. But actually, more such opportunities are coming, because if you see the advent of the electric vehicles, what we need is basically development of electric drives, power electronics. This is predominantly electrical engineers and electronics. But the vehicle engineering is predominantly mechanical engineers. It is still there. Structural engineers also there, thermal. And in EV, there is a big role for thermal management. And that also we've been working on for the past few years. For instance, if you look at a common architecture, if you see, at the system level, there is an architecture. So this entire is not just a thermal management. It's basically called energy management, because how to because storing all the energy in the battery, but how the rest of the vehicle uses, from the cabin cooling, heating, the battery cooling and heating, to powering all the systems and everything. So there's a system level energy management, and at the components, one has to develop new types of heat exchangers, pumps, compressors, fan valves, then the controlling system. So actually, it has given us more work now than it was before. So it has opened up new opportunities. Uh, so we have thermal management, not just of the batteries. When people talk about thermal management in electric vehicles, normal initial thought is that the batteries have to be cooled. Uh, but yes, there are a lot of opportunities to work in this field for battery thermal management, and there are many different types of cooling systems which have been invented, and there's so much to learn there, and use our laterally use other technologies. But thermal management of EV motors is also quite big now. Now, this was not a big problem earlier because the motors are not that powerful. Now, because of the kind of duty cycle demand, the motors have become quite powerful. So thermal management of the motors is also a big challenge. And thermal management of the power electronics also goes side by side, because earlier the power electronics in vehicles, the thermal management was not a big problem because of the limited nature of the usage of the power electronics. But now in the EVs or hybrid EVs, the control system is quite stringent and quite elaborate. And so the power electronics is also quite big. And we are already having some projects which I will just see. This is a thermochemical energy storage system for EVs, which I will describe in a little more detail. Here, it is actually for the batteries, it is not just the cooling. You will also need preheating of the batteries in cold climates before a vehicle can start. Now, this is basically an energy storage system, heat energy storage system, on demand heat energy storage system for battery preheating that we have proposed, and this system is nearly developed. Then use of passive cooling mechanism like thermosiphon for EV motor cooling. So we have one project. And from an industry, an automotive OEM, we have another project on thermosiphon based cooling of power electronics. So there are many such inquiries which are coming up now, which were not there before. So we are actually becoming more busy than before with the advent of the new or shift of energy usage type from one to the other. Now, while we are on the subject of the EVs, a long-standing problem has been the energy storage in the EVs. There is no doubt that the future will be electric transportation, and that has happened in the trains. It may also come to buses and other vehicles. In a small way, it has come now, and the main reason is that there's a zero on-road emission. But the question is that when we talk about EV, we automatically think about full battery EV, but that may or may not be sustainable. But nevertheless, the electric transportation is something that can stay. Now, why this may not be sustainable is because the battery storage, in the battery electric vehicle, the scaling up is a problem. For instance, a typical four-wheeler requires 500 kg of lithium-ion battery. Not 500 kg of lithium, but the battery weight is nearly on that order. Now, today in the world, there are billions of those vehicles. And if we set a target that all vehicles will become battery electric vehicles in the next 10 years or 20 years, they imagine it will be trillions of kgs of battery. And these batteries have life for few years, like 5 years, 7 years, or whatever, maybe more. And the recyclability is not so easy. So right from the mining of these materials to production of the batteries and then recycling and everything at the scales of trillions of kgs every few years, is a humongous exercise, and how much resource availability and how much of environmental issues will be there. Unless we do a scaled up analysis, we will not be able to tell. It is just like the case of the IC engine vehicles. When it first came up 100 years back, it was supposedly a clean form of fuel at that time, because the scale was so low that when they replaced the horse-driven carriages, the roads were not smelling of horse dung anymore. So people thought it is cleaner version, but it is only a matter of time when it is scaled up. Right? Even CO2 as an emission was not seen as an enemy until 80s or 90s, or even, I would say until IPCC brought out its report in the early 2000s. Before that, the emissions were limited to the NOx emissions and carbon monoxide emissions, sulfur dioxide emissions, and so on. But never anybody talked about, rarely anybody talked about actually CO2. But when it's scaled up, not just in vehicles, but other industrial production mechanisms, it's a scaling up which actually causes the environmental problem. And that's the time when we realize. So we need clean energy, not just clean energy, we also need clean storage. Now, that's the reason for the vehicles, hydrogen would be an alternative. Now, what is hydrogen electric vehicle? It is like a hybrid concept, that you have an electric transmission, but you don't have to store every storage, the unit of storage in the form of battery. You can store on board in the form of a fuel, which can be derived from a clean source. So that's the thing. So it can be like a hybrid vehicle. Fuel cell is one of the options, or it can also be IC engine based hybrid, and the source of, or rather the fuel for that IC engine can be hydrogen or any other clean fuel. But the issue is again storage. Right? Hydrogen storage is a big issue. So in summary of this part, what we can say is the electricity cannot be stored in large quantities easily, because especially big power plants like gigawatts of power plants we are having, we cannot have gigawatts of batteries. Then really it will be we'll go to some other problem. To solve one problem, we'll create another problem. Clean fuels such as green hydrogen, it can be easily stored, right? So indirectly, we are storing the electricity because the green hydrogen can be produced from the clean electricity. So it is called, a term has been coined, is called the power to X, P2X route, where X stands for the power fuel. So power is basically the electricity source, can be a clean source. And then to the X is the fuel. And this fuel can be hydrogen, is the primary extract by electrolysis. But one can also produce from other routes methane or ammonia, which can be more easily stored, or ethanol from biofuel. Methane, ethanol can be produced from the bioenergy, which is also labeled as clean. So these are the routes by which clean fuel can be generated and stored from renewable sources. Right. So a sustainable energy economy can be a mix of electricity and a clean fuel. So these are the two vectors, instead of all H2 or all electricity. Now this all electricity is what some people are pushing at the moment, and we need to look at the sustainability of that as well. And that is why parallelly this is also getting developed. And even ammonia as a fuel is also getting developed, and ammonia engines or methanol engines are also getting developed. But the infrastructure for the mobile sector is yet to be fully established for hydrogen and other forms of alternate fuels. Now, when it comes to R&D opportunities, the entire hydrogen economy or the hydrogen energy technology, there is a production, distribution of storage, and utilization for energy. And we have opportunities for contributing in so many different ways. In the production is electrolysis, thermochemical cycles, and so on. CO2 free energy sources, renewable energy, nuclear energy, so many options are there. In the transport and distributions, so much of development needs to be done in the pipelines, compressors, because this kind of fuel needs to be transported over hundreds of kilometers or thousands of kilometers now, like the way we have for oil or natural gas also. So we need to build this kind of infrastructure, and a lot of R&D is required. It's not that easy because hydrogen in embrittlement studies, corrosion studies, many things which are there which needs to be done, right? And utilization also in many in the form of IC engines or in the form of fuel cells. Especially we are looking at either a hybrid vehicle with this or direct IC engine based, fuel based, clean fuel based IC engines. So some kind of a cycle, a hydrogen cycle or energy cycle, like renewable energy sources or nuclear source can produce the hydrogen, and then they can be transported and transport and storage. And finally, there may be a combustion or conversion in some way or the other. And then when we do that conversion or combustion, water is produced, which again goes to the environment. And then we take water for electrolysis of the hydrogen. So this is a hydrogen and water cycle, sustainable cycle can be built. So these are just some ideal ways of looking at. Now coming to this green hydrogen, which I didn't talk about much, this is also a new opportunity for core engineering disciplines. It is not just electrolysis, which is basically the field of chemists. Even fuel cell or electrolysis, basically they are just the reverse of each other in terms of technology. You need the same kind of materials to be developed. There's so much of scope on the system level design. So in the hydrogen production, we have renewable hydrogen production by electrolysis and hydrogen from other sources like biomass and carbon control production of hydrogen. Then we have on the transport side, design and system analysis of the networks, pipeline storage, as I was talking about, transition from natural gas to hydrogen. Also, there's quite a bit of R&D which needs to be done. Combustion of hydrogen, engine is not so easy to make. So quite a bit of R&D needs to be put in there as well. Now, when you're talking about green hydrogen, the normal way of producing is you take the clean electricity, which is from the renewable or nuclear, and then this is a solid oxide based, as an example, and it requires very high temperature. If you see 750, otherwise the yield is not much. Now, what you do is, and also you need steam. Right, steam here, and then the steam is heated. A lot of this energy that is required is actually to convert this steam and making it a high temperature steam. Now, one thing we should not forget is that if so much of energy is required here, all the focus should not be only on this, that is the clean electricity. We can actually get, and this is a proposal which has been there and implemented in some places, that from a solar thermal, that is CSP, cogeneration, you take heat as heat and then use it to generate the steam. So in fact, you can make a high yield green hydrogen by having both the PV or wind at the same time solar thermal. Right. So these are some of the things. So this is just that's the hybrid approach where heat input can come from a solar thermal and the other electricity can come from the PV or the wind or the nuclear. Now at ISC, there has been some research. So I'll spend a couple of slides on this, on the production of the green hydrogen through the biomass route. That is Professor Dasappa's lab now, producing hydrogen and syngas from the biomass waste. And so this is basically the adsorption based pressure swing adsorption base, and one produces the the PEM fuel cell, or it can be used to produce methanol, then fuel, aviation fuel, ammonia, etc. It can produce. So this is already there's a pilot plant which is there in the lab to produce this, and potential for municipal waste also as a feedstock that also has been evaluated. And in that lab, which is called the Combustion Gasification Propulsion Lab, biohydrogen so there are already quite a few projects which are on stream, and some of them have been funded by the oil companies like IOCL and some multinational companies, and MNRD, of course, is one of the main contributors towards this. And then on the hydrogen storage technologies, we have there's a physical based storage which is well known, that is compressed tanks, very high pressure like 350 bars, which is type 3 maybe, and maybe 700 bar for type 4 tanks, cylinders, composites there. Then liquid hydrogen or cryo compressed hydrogen. Now these require very low temperatures. This requires very high pressure. And then there are material based, which are the sorbents, metal hydride. Conventionally they have been used, but they have not been that successful, mainly because of the small weight percentage of hydrogen storage. So it becomes bulky as well as heavy. Now there are new types of materials which have been invented, the high entropy alloys. There the weight percentage can be reduced, and also their operating temperatures can be tuned for operating at room temperature, near room temperature. So then they will have a clear advantage. So that is another type of work which is going on in many places. That is a material-based storage using high entropy alloys, or maybe other sorbents with very high surface area, like MOFs, but they are quite expensive now. So, and now the benchmark, let's look at it. So at one time, the benchmark was so if you take 200 bar, compress it, then this is too big to fit into the vehicle. This is the liquid, but liquid, the infrastructure for that on a mobile vehicle is very difficult. And these are some of the metal hydride based, but they require high operating temperatures. Right, and that is where the high entropy alloys come into the picture. So this kind of sizing can be done. Right, but previously, see, the weight was compared with the weight of weight and volume of a fuel tank of IC engine. But now the new benchmark of weight has changed to the battery electric vehicles, because already vehicles are carrying a huge amount of batteries. Just as an example, if you show that this is a Tesla Semi, like full battery powered truck, and out of a total, this is a range of 500 miles. Out of it's about 20 ton, 25 ton truck, about 4.6 tons is actually the weight of the battery pack. Now, if one proposed, 10, 20 years back that I would have a material-based hydrogen storage, which would give me that kind of a range, which would weigh this much, it would have been rejected. But now this is a benchmark, so this kind of weight is accepted now. And if we do a calculation of even with something like metal hydride, conventional metal hydride, which is not a very good performance in terms of weight percentage storage, like on the order of 1 to 2, even then, this turns out, about 2600 kg to have this kind of a range of 500 miles. So there is scope now. There is scope if the material is improved, not just this normal metal hydride, but with some better high entropy alloys or other higher weight percentage storage, it can be done. So the key to success is, of course, the appropriate design of the reactor, the heat and mass transfer studies, scaling, optimization, heat recovery technology. So there are a lot of scope for R&D which can go in. Simply one cannot think and just put it like that. So it requires a lot of effort. Now, I'll spend just a few more minutes on our work on thermal storage and sorption-based hydrogen storage. Since we are talking about material-based hydrogen storage, we started our work on actually thermal storage and on to hydrogen storage, and we are still working on it though. Now, when you're talking about thermal energy storage, which is sorption-based, what is the main advantage? Right? See, there are sensible heat thermal storages, because thermal storage is also an important part in this whole game of renewable energy based economy. Not just fuel storage, but also heat storage is important in many applications. So that's why we need to look at that as well, especially long-term storage is very important. So sensible heat storage is very old, but although the technologies are well developed, sensible heat means that without any phase change. So, but the storage has to be done at higher than ambient temperature and heat loss over time. So only for a short time you can store energy, because heat will leak out eventually, even through insulation. Latent heat storage has a higher energy storage density because there is a latent heat associated with the phase change of the materials. Right? So these are also well developed, but again, heat loss is an issue. So for a long term, it can't be stored. But short term, for a few hours, it is good. There's another storage, which is thermochemical energy storage, which uses reversible exothermic and endothermic reactions. One can use salt hydrates, one can use metal hydrides, ammoniated salts. There are many, many options. Okay. And what one can do is not just high energy density storage, but storage at ambient temperature one can do. Now, how one can store at ambient temperature heat is very intuitive, and I will explain to you here. This is how it is done. The fundamental principle is the thermal energy is stored in the form of enthalpy of the chemical reaction. So which means that when we have two substance, there is a compound, or rather a material can be combined, and if you apply heat, you may be able, as an endothermic reaction, you may separate out A and B, and now you can store A and B separately. Okay, and then whenever you want, you can bring A and B together and it will produce the heat. It's an exothermic reaction. So this is, it sounds very simple, but and advantages, of course, high volumetric energy storage density, long-term storage without the losses, ease and operation control, wide range of temperature and pressure, and so on. And there are many types of materials which are ammoniated salts, salt hydrates. So we have used salt hydrates like K2CO3, and we have also used metal hydrides in this one. And there are other also which can be used, which are based on pure chemical reactions. Now, this is easier said than done, how it can be done. Now, the operating cycle, I'll just explain how it is done. So if you have a hydrated salt here, salt and the hydrate, it's in the form of hydrate. The application of the heat separates out the water vapor part, and the water vapor comes here, and then with ambient energy, or rather cooling, we can cool it and condense it and keep the water separately. So this is this part of the cycle that is called the dehydration. And then when we want the heat back, all we have to do is we take heat from ambient, make this evaporate, and the water vapor comes back, and then forms the hydrate back and releases the heat. And that heat can be taken away, whatever be our usage, it can be taken away with a heat transfer fluid. So that part is called the discharging process. So this kind of system we have developed. Of course, the advantage over here is that you can, I'll skip this part because this will take a longer time to explain. Now, what we have done is we have done design of reactor using scaling analysis, because there are so many challenges over here, because the salt or the adsorbent is kept in this bed. This is a packed bed type of arrangement, and this is the heat transfer fluid which supplies heat during the charging of the heat, and it takes away the heat when it is discharging heat. So all the length scales, time scales, because kinetics is also involved in this one. And that's why the time scale comes into the picture, because we need to design it for a cycle time. So vapor flow rate through the bed, and we do CFD analysis, and I will quickly go over. And we have now created an experimental setup to prove this concept of energy storage by thermochemical means. And so we have done our experiments. So this is the source of heat that we use to store the energy. So this is the dehydrating or the charging process of the heat. And then when we wanted to discharge, we take ambient heat and then we recover the heat. So we may not recover it to the extent that the same temperature as we had stored, because this depends on the ambient temperature or it depends on the vapor pressure at that temperature, vapor pressure of the system. So nevertheless, it can be stored, this heat can be stored over a long period of time and then delivered at the point of use whenever we need. So it has, as I was mentioning, in the case of electric vehicle, any electric vehicle thermal management system, they also have a heater. As a backup heater is basically to preheat the battery when the vehicle is parked in a cold climate, cold environment. So this heater is normally an electric heater. So you need to park the vehicle always at a garage or some other source where there is a plug point where this heater can be operated. Battery gets preheated, and once it reaches around 10 or 15 degrees Celsius, then the battery can be, the car can go. Otherwise, if you do a cold start, it can damage the battery even more than by heating the battery. So battery, both cold, low temperature as well as high temperature, is not good for the battery. So instead of, now with this present arrangement, all the vehicles had to be parked in those places. But with when we replace this with a thermochemical system like that, then what happens is we can have an onboard thermochemical energy system, thermal energy storage system, for an emergency heat source to preheat the battery, start the car. So advantage is that the car can be parked anywhere without risk to battery health. So this is not there in any car now, but we are just proposing something like this. And the other project that we have done, this is the last part which I'll do, is a metal hydride based thermal energy storage and hydrogen storage. Now, metal hydride based storage, the same thing as the, so when you have the metal hydride, you apply heat, the metal or the alloy and the hydrogen gets separated. Now, if you can store them separately, this hydrogen, and bring back the hydrogen, and then it produces the heat. So this is from the point of view of a thermal storage, right? Now, as a result, what happens is we need, there's a wide range of materials and properties like high temperature materials, medium temperature, low temperature. For the hydrogen storage, we need the low temperature or near ambient. And I'll tell you why, is because it is that suppose we have this system over here where we apply heat, and the heat source can be from anywhere, from renewable to other waste heat. And so the hydrogen gets separated out, and you need to store the hydrogen. If you store it in a tank, the volume required will be too high. So what we do is we store it in another metal hydride. It's different from this one. Now, the advantage is that this low temperature metal hydride, you can release the hydrogen back even by taking ambient, near ambient heat. So, so that when the hydrogen comes over here, it produces the heat back. So in this way, we have developed two types of systems. One is the energy storage, which is this hydride system, and the other is one is for hydrogen storage. And of course, this is the thermodynamic diagram, like Van 't Hoff plots to calculate. So there are properties which are required for energy storage, and the metal hydride that is required for the hydrogen storage, it will be quite different. Because this one you need high heat of reaction, this one you need a low heat of reaction for the hydrogen storage, because you need energy to discharge also here. So this is the high temperature, this is the fast reaction kinetics also you need, and low hysteresis. These are some of the properties. So there are a variety of metal hydrides. So what we do is we choose a system, one for, let's say, the hydrogen storage, which is the high temperature material. This is 1 over T, 1000 over T. So temperature is decreasing in this direction. And this is the pressure. So this is the high temperature Venn diagram for the high temperature, medium temperature. This is high temperature. And these are the low temperature ones. So, okay. So this is now the cyclic operation of the two beds. And okay, Professor Acharya, do I have a few more minutes or I'll wind up?
It's okay. Please.
Okay, I'll wind up in a few minutes. Yeah.
No hurry.
Okay. So this is a cyclic operation of the coupled beds. Now, coupled beds, what is happening is, this is for the higher temperature. So we are bringing in heat here. Hydrogen gets released and flows into the lower temperature hydride and gets stored over here. So this is called the charging process. And then the discharging process, we bring in room temperature heat. And so this is such a hydride which can dissolve even at room temperature. And then the hydrogen flows over here and combines and forms the hydride and releases the heat. And so this is the cycle diagram of charging and discharging. This is 1000 over T, so the temperature is decreasing in this direction. And this is the equilibrium pressure. So with this cycle, we have done some CFD analysis of this two-bed system, one high temperature reactor and the lower temperature reactor. And after doing the CFD analysis, we have, of course, validated, did an experimental validation and tested the system in the lab with a hydrogen storage supply facility, and it agreed the performance of how much of heat got stored and delivered, that also more or less matched with the theoretical prediction. So and this was, of course, supported by Gale. They wanted a system for waste heat storage system, long-term waste heat storage system. So we scaled up the system, and we did this project in our Chitradurga campus, where we had source of solar heat to be used for the thermal storage. So we did. So these are the two reactors, one the high temperature reactor, the other is a medium temperature reactor. And these are the reactors which are for hydrogen storage down below. So this is a full system where we have the initial source of heat is basically solar dishes. And these solar dishes, which are basically Scheffler dishes, which supply the heat, and it goes through a heat exchanger where it, in the solar dishes, actually, it's an oil that gets heated, thermic oil. And that oil to air heat exchanger we have, and then hot air we bring, and these are our thermal storage reactors. This is a high temperature reactor. This is a medium temperature reactor. So the hot air dissolves the hydrogen, and it comes and gets stored in these hydrogen storage beds, which are low temperature based metal hydride reactors. And so this is the way the cycle is. And when we wanted the heat back, of course, it is heat is supplied to this. But here, the heat, the grade of heat that we, a low grade heat, like little bit above ambient or ambient temperature, is good enough. And then we get the heat back over here. So this is the cycle that was proven, and it was delivered. Now the last part of it is, what are the opportunities in industrial process decarbonization, especially places where there are large number of steel and cement plants and or aluminum plants. This has become very important now in our country also. Quite a bit of work is getting started, but nothing much has happened yet. So there's a lot of opportunities. So the 4 pillars of decarbonization are energy efficiency, industrial electrification, low carbon fuels, and the carbon capture. So what are the temperature ranges, right? What are the temperature ranges if we see that a large amount of heat energy is actually the low temperature range, if you see, up to about 300 degrees. And the high temperature range is basically iron and steel, aluminum, cement, and so on. So what it means over here is that if we use electricity that is generated from renewables, it is, and then we are going to use for this kind of application, which requires such a low temperature, then it is not a good thing from an exergetic efficiency point of view. But that's what's happening now. So that's where I think some corrections need to be done. So because here one can use heat as heat captured from solar directly, it's better. And these are the areas where high temperature is required. So here using electricity to generate the heat or using fuel to like hydrogen fuel or any other clean fuel is the appropriate choice. So unfortunately, the way the world is moving, it is either all electricity and fuel based or nothing at all. So we need to bring in heat as heat by some means for these kind of applications, even in the food processing as well. And in the case of special, because in India, iron and steel has become decarbonization is very important. And the reason is that, for instance, the EU, European Union, has already declared that unless the steel is produced by green means, it's a green steel going to buy, or the tariffs will be very high, something like that. So obviously, to stay in the market, everybody needs to now change over. So there's a hectic activity now going on in many of the steel plants, including Tata Steel, to move towards decarbonization. So that means that we need fuels and process heat solutions, and we also need waste heat to power, because a lot of waste heat gets generated in steel plants and cement plants, which can be made use of. So there are opportunities here as well. Implementation of low carbon hydrogen in the direct reduction, DRI stands for direct reduction of iron ore. There also is quite a bit of scope is there. And this is just a slide from Niti Aayog. No, not Niti Aayog, but Statista, about the distribution of greenhouse gas emission in India by sector. The power sector greenhouse gas emission. Agriculture is quite big. I don't know exactly, I'm not knowledgeable enough how one decarbonizes that part, but maybe we are helpless. Manufacturing is still a big sector. So targeting manufacturing and decarbonization is a good step. And targeting power generation we will solve a lot of problems. In fact, transport is a smaller sector in terms of the greenhouse gas emission. But nevertheless, if one applies all the clean fuel techniques in manufacturing or in power generation, one can apply that in transportation also and reduce it. Building is also another one which also needs to be looked at. So the current approach in India is, of course, through the hydrogen mission, quite a bit of work is going on from electrolyzers, and that's linked to green electricity. There's an opportunity for biomass as well, which is being looked at, and opportunity for direct use of renewables or hybridization. So I think what I'll do is I'll stop at that, conclude that engineers must play a significant role in accelerating shift to a sustainable future, low carbon technologies, use their knowledge to optimize renewable energy system to maximize the production efficiency and dependability. Then we need to use our ingenuity and technical know-how in the creation and use of clean energy solutions. So it's not a simple solution. It's a complex web of things that are happening over there, and there's a lot of clutter. And so a comprehensive view is very difficult to create. And but we still should find solutions which are sustainable for with cutting edge engineering solutions. We should work towards the next generation or sustainable future for the next generation. So thank you very much. These are all my collaborators from institute. There are many other students. Only those who are directly related to the work.
Thank you, Professor
Thank you
Dutta,
very
for
much.
your excellent lecture.
Yeah, I will.
I'm sure actually all participants would have really enjoyed it. And
Thank you, sir.
Now actually we'll have a few question and answer.
Okay, shall I unshare now? Or?
Yes, yes.
Okay, thank you.
Please.
Thank you, sir.
Yes, Sanat Kumarji, you are mute. You are mute.
Now I should be listening. Yeah, okay. I always forget that.
Yes, yes.
Yeah. Sir, I'm very, I noticed that you use the word heat as heat. Use heat as heat. That was a very good idea that I am able to understand and accept also. But today, say supposing you take metallurgy or steel making, we use heat to produce electricity and electricity to produce heat, which is not a very good thing at all, according to me, is it not? So, how do you generate the required amount of heat for metallurgical operations? That's a very high temperature heat. Now, you also said that superheated thermal cycles are coming. Superheated thermal cycles are okay, but for getting that superheat, particularly in the nuclear sector, to get that one, you need materials that will withstand that high temperature in a reactor. At the moment, it is not there. But anyway, that was only comment. My question is like this. Anytime you are converting heat to electricity, you are releasing some energy back. It may be low grade or anything. You are releasing some energy back to the atmosphere. You are increasing entropy of the earth. What happens to that? It is not, it cannot go back to space. It cannot. So ultimately, the entire earth will become very hot. Well, am I right or wrong, first of all? And what do you do about it?
Sir, you have hit the.
You are not only releasing chemicals, you are also releasing energy, heat energy. You are releasing useless heat energy.
Absolutely. So you have hit the nail on the head, sir. There's one comment I would like to make is that when we are using electricity to produce heat, as I mentioned, there is huge loss of exergy. Basically, we are generating entropy, and directly or indirectly, we are damaging the environment. Only place where we may be excused to doing so is if the heat required is of very high temperature. If this is very high temperature, the grade of that heat and the grade of electricity is very similar. Because if you go from the other side, very high temperature to work or electricity is also, the conversion rate is quite high. So similarly, one can excuse. So therefore, for a high temperature metallurgical process like steel making or cement making, if the temperature requirement is high, then using of green electricity for the purpose is, I think, it's not a crime. But where I am having a problem is that there are many applications, which is the bulk of the heat usage is actually in the lower temperature, like 100 to 200 degrees Celsius,
Exactly.
Including food processing, right? Many others. And that is where I think it's a big loss. Even from fuel to heat is also a crime, because fuel is also high grade energy. Because one can produce very high temperature with the same fuel, if you burn it. But we are using it at 100 or 200 degrees Celsius. It is not. So the solution is only where one can use waste heat, because the same steel plant, there may be lower temperature processes. It can take, that's the lot of it is heat recovery one can do. Same thing in the food processing industry. There are certain temperatures which are high. I mean, certain operations which are higher temperature. One can use electricity or fuel, but the lower ones should come in the form of heat recovery. And then there are places where one can generate up to a scale. One can generate solar thermal heat with a low concentration. Then low concentration means like, with the lowest concentration or without concentration is what we have hot water in our the rooftop, for our bathing. Hot water is that is without any concentration. That is the best way to use heat as heat. But but big industrial processes, locally one may not be able to generate that amount of heat by solar thermal means. So that is where the problem comes. But what I'm seeing is, just to add to this, in Europe now, Europe and some places, Canada also, they are doing it. They are, even for household to produce hot water, they are saying they are converting the PV electricity to heat. So my question to them was that, along with that PV, why not also have a hot water collector, solar thermal collector, which is very cheap. Yeah, very, very cheap also, and environmentally sustainable. Is glass and metal only. So to the extent possible, why not do that? But they said that no, there are limited amount of rooftop,
Exactly.
because PV we are investing on anyway. So might as well use that. Then use heat pump to heat the household. So all these things are there. So there are a lot of factor of convenience, and all these things also people are using to do this.
Okay.
What was your other question?
Yeah, I have one more question. It is like this. I'll start with an analogy. In hydraulics, we have high flow, low head. By using a ram pump, you can use it a high pressure, low flow.
Yes.
That means you can ratchet. So is there a way of ratcheting the heat, low heat, to collect a lot of low heat and convert it into high heat? Some loss will be there, but can it be done? That is
yeah, only it's a good idea, but only thing is that in thermal, there is no such direct conversion, because in hydraulic, the head is also the high grade. The grade is not changing. It is only your mechanical advantage that is just like a lever. It is happening, like with a mechanical advantage. So there is no conversion of energy. It is only a conversion of head.
Okay.
Whereas when you want to convert energy from heat to electricity, always that that Carnot efficiency will come into the picture.
No, you convert heat to heat only. That is ratchet up heat. That is low grade heat is there.
No, that is
abracadabra, and then keep it up a higher level. I have not come across
to upgrade. We can do. We have that upgradation of heat is possible. In fact, that thermochemical energy storage which I showed, there is a way to upgrade heat also.
Okay.
Anyway,
I have to read up more about it. I have to read it up.
Yeah.
Long ago.
Yes, to some extent it's possible. It's possible to upgrade heat.
Thank you, sir. Thank you.
Okay, thank you. Nice question, sir.
Any other question?
I think
Renu Sharma, please,
Dr. Abhishek.
Yes, those who are having question, they can unmute. Or I will...
Good evening, sir.
Abhishek,
can you hear me? I'm Abhishek Singh.
Yes, I can hear you.
Can you hear me?
Yeah, I can hear you.
Good evening, sir. Thank you so much for such an enlightening lecture. I have a very rudimentary idea about clean energy, and I was invited into this lecture, and I'm thanks to you, I have a fairly good idea now. I work with the government in the transportation sector, and but I'm not directly into energy. So I have a few rudimentary questions. Sir, you had shared a slide in which you described the levelized cost of entire lifetime, right? So in the transportation sector and also all over India, we see a lot of hue and cry about going into the solar sector. Now, from the curve which I see regarding the cost, I see the solar was about $350 at around 2009, and it has dropped down substantially up till 2023. Do you attribute this cost to be the primary reason for us to go into the solar sector?
Sorry, if I understand your question, is
So the cost of materials has gone down as per the curve which you had shown.
yes,
The
yes,
LCOE curve, right?
yes,
It dropped down from $350 to a substantially low amount by 2023.
yes, yes.
So was this the catalyst? Was this the driving point for our country to go towards adopting more of solar power as against the non-renewable sources of energy?
Yes, that was the driving. I mean, always see the adoption of anything. There, it has to it has to make a good business sense. So if the business model works out, only it will be done. So only when the cost of production of that. Now, only thing is that it was not produced here. It is produced elsewhere, and so most of our solar panels, either the panels are imported or the key components are also imported. Solar cells.
Sir,
But so the
so
world cost when it came down from other countries, so
Yes.
we have adopted it. So it makes sense from a business standpoint.
It does make sense, but sir, don't you think that production of solar glasses for solar panels, production of glass itself is a very much is a big contributor towards polluting the environment?
No,
And
it
this is
is.
one of the major. I have discussed it with Borosil Renewables. I have discussed it, and they are somehow they could not give me a convincing answer how will this be an advantage over that.
No, it is. It is. That is the same thing with the batteries and everything, that what we and in the background, it may not be as clean as we think it is. So it is always, that factor is there, because to produce anything, it's a human activity that we are adding, and any human activity will contribute towards damaging the environment to whatever extent. So, I actually have a saying. That's why I become unpopular. I say there is no such thing as clean energy. You can only have a cleaner energy.
Yes.
One can be cleaner than the other, but there is no such thing. So therefore, our aim should be always to reduce the usage of the energy, right, and produce it in as clean way as possible. So there is no. But the way things are going, especially with the artificial intelligence, the digital economy, the need for energy is going up, skyrocketing. But they are saying that, okay, it doesn't matter because we'll produce clean energy. We'll have more solar, more wind, and so therefore it doesn't matter how much we use. So that is a kind of thing, we have to stand up against. Right. But unfortunately,
Thank you.
So I have three small questions, if I can be permitted, because all are linked. I'm really sorry to take some of your time, but I'm very
no,
much
I'm fine.
interested in knowing this.
I'm fine.
Ma'am,
Yeah, sure. Please.
Yeah,
kindly
with
allow.
permission of chair, we can do it.
Ma'am. Sir, you had described a term called as EROI, which I think I understand. And you said that in the world they have come to a conclusion that generally a breakpoint of 7 and above is the established norm, right? But I just wanted to understand why not, sir, greater than 1 or greater than 2? Why 7, sir? I couldn't understand that.
Yeah, it's a good question. It is basically, it's not that the world has accepted 7. World has no norm on this one. These are all parallel analysis that is being done, called sustainability analysis. So, of course, if it is less than 1, it is a failure. But greater than 1, you are at the end of his lifetime, it is producing some net amount of energy. But so what, which means that you have invested so much, and then you have, created a problem to the environment, and at the end you are getting only very little return. So we are doing more damage than the benefit that we are getting. So the 7 comes because there's an opportunity cost to everything. So factoring all the opportunity costs, if you see all the investment, because these kind of investments can go into so many other sectors,
Okay, that
healthcare,
will push it
education,
much above
everything.
one. Understand?
Yeah.
That will
So
push it much above one. Okay.
yeah. So in totality, and how the investment could have been used versus only on producing this energy.
Okay. Sir, I have a tangential question. I have friends at Delhi Metro Rail Corporation, and they say that they are too much invested into solar power, and they went to the extent of saying that they are deriving a lot of solar power from a very big solar plant at Rewa in Madhya Pradesh, and they have signed a memorandum of understanding with government, in which the government will prioritize sending power from Rewa plant to DMRC to operate their things here. Now, the person told me, and the person I rely on that person, he said that about 8% of the total power used by the corporation comes from solar. And out of that 8%, now the total 100% power, some is traction power, the power which is used to run the trains. Another is non-traction power to run the offices, to run the systems, to run everything. So, my question is, won't drawing power from Reva be much costly because of the losses to get the power from there to here? I have no understanding, but this is the first thing that came to my mind. What about the losses? Why does the corporation want to draw power from so far away? Isn't this akin to electricity losses when we get power from the hills?
That I don't understand. See, of course, um, how the grid works. So there could be trading which is going on. That power can be traded, so that same power from that source to the point of use, the same electrons may not come. So it is basically it's a trading arrangement that can be there. That
But sir, can we
notionally,
use solar power actually for traction purposes? You said about high area, concentrate that into low area. You talked about a very good concept which I did not know. I had written it somewhere: high grade and low grade. So solar is high grade and electricity is low grade. So we would be needing a lot of
no.
solar power. I think
The
I
other
may be
way.
wrong in my
To add
understanding.
here, Sanat sir
No,
wants to
the
add.
other way. The solar is low grade. As it received on the earth.
Yes, so
Electricity is the
we need
highest
a lot
grade.
of solar and go to electricity. It will involve a
Yeah.
lot of cost, at least for the railway sector, if I'm not wrong.
Yeah, so they will use, so the advantages to use a grid power. Now, what can happen is that the grid gets fed by all means, from all sources. Now, so the notionally, when I'm saying that I'm using the power from Madhya Pradesh, but I am sitting in Delhi, it could be some kind of a notional arrangement, trading arrangement, that I am supporting that, and that is the power that I'm using. So somewhere it gets accounted for. So it is not a dedicated line. I doubt it would be a dedicated, power line which would be coming from there to the point of use.
Okay, because
Sir,
I read
I have got
Yes,
an
sir.
answer for his question. Maybe you
Sir,
can
please.
consider this. What sir said is right. Rolling of electricity from one place to the other and the other fellow transfers. That is a standard
Sir.
method they use. But also, if you use high voltage DC, HVDC transmission, you can reduce transmission losses very much. So, for example, if I remember right, from Assam, they have laid a HVDC line. So, once upon a time in India, this HVDC line laying was a very big project. I don't know where it is from Madhya Pradesh to Delhi. But if you do that in HVDC, the line loss is quite less. We could control that. But the rolling of electricity that he said is also a correct solution. Thank you.
Rolling of electricity. Okay, I'll search about this. I have no idea.
I don't know whether that is the correct terminology you have to use.
I don't know the
But
terminology, but it is an
it is
accounting.
rolling. I have heard
Yeah.
these people use the word rolling. Rolling, they roll the electricity from place to place.
Okay, I'll read about that. I am done with my questions. Thank you so much, sir. Thank you so all of you for answering my questions.
Sir, I am Tripathi here. I just wanted to say that we call it wheeling charge or we call it by displacement. So you inject some place and it is accounted for at another place. Just like RPO obligation in solar, Odisha gets a RPO deal with Rajasthan and Gujarat. Plants are set there, and we pay for that because we think that instead of putting it in our place, it is more economical to put it the other place. So as you said correctly, sir, I mean the grid power will be used, but grid will be strengthened by a lot of solar power. I just wanted to ask one question, sir. What is the future of this fuel cell? I mean, I was in BHEL. We had a 50 kilowatt fuel cell in Hyderabad, if you remember. It was a disaster, and we never got any profit or keep it running. It was not sustainable. So whether phosphoric acid or alkaline or solid state, I have been hearing that not more than 1 kilowatt fuel cell is commercially available. Why is such a stagnancy in the chemical field? Why are we not able? And they say that luxury cars are being run in France, and we are also hoping that we will run our vehicles in Leh and Tibet in fuel cell. All of them will be imported, or it is just we are lying low on that area?
At the moment, most of it is imported because even our solar panels, basic ingredients are still imported. Fuel cell also be imported. So import point of view is another issue, which I don't want to open up now. But coming to that, see, fuel cell for a lower scale application, it is very well established. But at the higher scale, the stacks, when the stacks become bigger, then at a system level, there are issues which needs good engineering solutions at the system level. But otherwise, the technology is well established, and right now it is also expensive for various reasons. Considering the reliability issues and all, and then they are produced in small numbers now. So eventually it will come, but fuel cell is not the only solution. The IC engine based on the same fuels is another solution. So both are being worked on parallelly. So ultimately, basically, you need electricity to be produced from the hydrogen. So one can use IC engines also through a generator. One can produce the electricity. Right? So there are many pathways now. So that is.
Any other question?
Sir, one question in the chat box by Shiv Bharadwaj. How many cycles of use are possible in metal hydrides?
So it's a good question. Any of these material-based storage solutions, whether it is thermal or whether it is gas storage, it is always, the stability of it has to be looked at. Typically, these are depending on, if it is hydrogen storage, that means always fresh hydrogen is coming from a source and it's an open system. Then the number of cycles can be less, but still about few thousands one can design for. And then after that, one has to reactivate it. So material is not destroyed, but there may be some impurities which could be coming up, or morphologically they could be transformed to something, though the performance can deteriorate. So the reactivation periodically has to be done, just like engines need to be done. These are also, it's a good question. So there are things.
Sir, I'll ask one small question.
Yeah, please do.
Like how can biomass be effectively utilized as a feedstock for producing green fuel like hydrogen? And what advancements are needed to make this process more sustainable and commercially viable?
Okay. It's a very good question, but I'm not the expert. Essentially, I'm not the expert because it's some of my colleagues who work on biomass. But essentially, biomass, there are two routes, either a combustion route or you can do a gasification route. So it's a gasification route which will produce the kind of fuel one can make. One is called the syngas, basically synthesized gas. So earlier biomass syngas was produced as a fuel, but now exactly I don't know the reactions, but it is possible to produce the hydrogen, because that energy is there inside, because biomass is actually it's a fuel source. So you are converting it to another form. The exact reaction and chemical reaction, I don't know.
What I have read, sir, Tripathi here, what I have read that blue and gray hydrogen production is a bit cheaper than green hydrogen.
Yes.
That is why it will get one, I mean, people will prefer it in some cases, converting to ammonia, storing it and using it. Pure green hydrogen today is very expensive. Using electricity to produce through electrolyzers, electric power, that is very expensive, although green, but blue and gray also have a future. I mean, biogas, if it is available in plenty, and that sink gas, what you said, with hydrogen and natural gas and H2 injection, H2O injection, water injection, substantial gas can be used for non-preferred areas,
Yeah.
but in bigger quantities with lower cost. Storage is easier, it seems.
Yeah.
Look.
Yeah.
I have actually a couple of observations.
Yes, sir.
It's not actually questions. I would just like to put it here. First of all, you said that actually this greenhouse gas, agriculture actually contributes substantial amount, but there is no way that it is being controlled or whatever it is. The real problem actually in our country is our rice production and jute production. So there we produce actually huge quantity of methane. So unless actually we can reduce water consumption in this type of crop or stop cultivating such type of crop, nothing much actually could be done on that thing. This is just an observation. The second observation what I have is, particularly for high temperature applications, we are talking that actually this hydrogen or some other thing actually cannot be, is not actually not being used, but the fact remains, ArcelorMittal plant in Canada, they tried to use actually hydrogen from whatever source it is for steel making, because that is being used as a sort of fuel, so it can be used as a sort of reduction agent and also for oxidation purposes. So, but what happened really, the cost became prohibitive, so it was not acceptable. Third point which I'd like to say, that whatever way that we are doing is, the way that amount of heat actually that we are rejecting, and also the greenhouse gases that actually we are rejecting, our entropy is increasing, our temperature is increasing, and it is estimated that in next actually few years, maybe by 2070 or so, the temperature, average temperature in Earth, it will go up by 1.5 degree centigrade. And with that, what is actually going to happen is that our, first of all, actually this coastal area will be flooded. The worst thing that is actually going to happen in India, it is predicted that the monsoon now will actually shift to the west coast, to Arabian Sea, not to, our Bay of Bengal. So there is actually a risk of this side of the country becoming really desert in the long run, and let us say Rajasthan and beyond, those areas, they will be flooded. So such a huge risk is actually there in this thing happening. So it is absolutely necessary that we have to find out some way how actually the temperature increase could be arrested. Otherwise, actually, it will create really a lot of problem for all of us. These are all my small observations. Whether it is of any use or not, I do not know.
All are important, sir. All the observations are very important.
Don't use air conditioners, maybe one way, sir.
Pardon?
Don't use air conditioners.
Reduce or at least keep it at a higher temperature, like 28 degrees or so. You will be comfortable reasonably enough. At the same time, you can reduce usage. I mean, there are so many ways of reducing, the electricity consumption, but the world is not going in that direction, unfortunately.
See, our country is becoming more and more affluent. So everybody wants air conditioners. Oh, you have to reduce use of air conditioners. That is I think, one of the biggest contributors to the heat in the earth.
On the lighter side, actually, age has also some effect. For example, say older people like me and you, we do not use much of air conditioner, even if there is air conditioner only for the guest, but we don't use it.
That's true.
So now, I request actually all who are present to please switch on your video. We can take a photograph. Anyway, those were, yes. Please actually take a photograph. Actually, this side it should be on the full screen.
No, it should be gallery mode. I think there is a view. You need to go to the gallery mode, I think.
Okay, please take in whichever way it is coming. Now, Professor Dutta, actually, I have got one or two other things to request you. If you really permit, then can we really share your slides to YouTube, so that actually we are thinking of bringing a sort of a booklet where all the lectures that actually we have taken, those things actually will be available. And of course, there will be YouTube link in that, so that anybody who is interested could listen to your beautiful lecture. Is it okay, sir?
Yes.
Oh, thank you.
You
thank
need
you
to
so
know
much.
how to do it.
Yeah. Now, I will request Professor Renu Sharma to please propose a vote of thanks. Before that, I would like to say on behalf of this INA Bhubaneswar chapter and SOA University, a small memento will be sent to you by post. Okay?
Thank you.
Thank you. So please actually propose a vote of thanks for such excellent lecture.
Sir. Honorable Chairman, INA Bhubaneswar chapter, Professor Damodar Acharya, sir. Esteemed District Guest Lecturer, Professor Pradip Dutta, sir. Esteemed fellow INA members, distinguished guests, faculty members, and dear students, it's my privilege to extend a heartfelt vote of thanks on behalf of INA Bhubaneswar chapter, Shiksha Anusandhan deemed to be University, CSIR MMT Bhubaneswar, IIT Bhubaneswar, NISER Bhubaneswar, and IEEE Bhubaneswar subsection for enlightening 48th lecture in the distinguished lecture series, sir. It is our deep honor to have Professor Pradip Dutta, sir, professor at Center of Energy Research, Department of Mechanical Engineering, IISc Bangalore, delivered today insightful lecture on transition to energy, clean energy, new and R&D opportunities for engineers. Professor Datta, your expertise and forward-looking perspectives have illuminated the path for we engineers and the researchers striving to contribute to the sustainable energy future. Thank you, sir, for inspiring us with your vision and in-depth analysis of emerging opportunities in clean energy, rather cleaner energy research and development. I express my gratitude to our dignitaries, including esteemed fellow members, and members, academic leaders, researchers, faculty members, and our co-hosting institute for gracing this event with their presence and engaging the participation. Lastly, I extend my appreciation to the audience whose enthusiasm and thought-provoking questions enrich the discussion. And sir, your engagement enforces the importance of collaborative efforts in addressing the challenges and advancing the cleaner energy solutions. Once again, I thank you, sir, for presenting a wonderful lecture today and giving us insight and motivation for today's lecture for fostering innovation and contributing to the greener and sustainable future. Thank you. Jai Hind, sir.
One more
Thank you.
actually small announcement
Thank you.
before we close. Two more lectures are now scheduled. One is on 4th of December and the other one is on 6th of December. So please actually mark these two dates, and of course the usual things will come for 4th as well as the 6th, so that actually we can attend in large number and make this program successful. And that will also mean our 50th lecture will be completed on 6th of December.
Thank you, sir.
Thank you so much.
Thank you. Thank you very much.
Thank you. Thank you, sir.